This video is going to look at section 7.4. It's about ionization energy, and then we're going to also go into section 7.5 very briefly at electron affinity. Ionization energy, we can abbreviate IE, is the amount of energy needed to remove an electron from an atom, okay? And it's always going to be a positive value because it's always going to require energy, okay? So we say that the change in energy is going to be positive because it's going to require energy. And the way that we can represent this is, well, let me take a step back. We're going to want to use a gas when we look at the ionization energy involved in taking an electron away from an atom. We want to use a gas because when we're dealing with gases, there's really no interaction with anything else. So we can't say, okay, well, we're going to try to ionize a species in a liquid or in an aqueous solution because whatever result we get, we cannot be certain that it wasn't from an interaction or an attractive or a repulsive force from the other species that are in that sample. So we can look at a gas when we do this. For example, I'm just going to move this up. For example, we can look at lithium, all right? We say that we're starting out with just lithium gas, and if we're ionizing this lithium, that means that we are going to take an electron away from it. So we end up with lithium plus, we end up with lithium plus 1, or just simply plus, and that's still going to be a gas. And then we're left with this electron that we have kind of plucked off of the atom. Another way of writing this is if we take a look at the electron configuration involved in lithium. We have 3 electrons in lithium, so remember when we write this, our energy is going to be increasing as we go up. We're going to start out with our 1s orbital, and we're going to go 2s, and then obviously we can keep going with this, but because we only have 3 electrons, we're only going to need these 2 subshells. So we have 1, okay, really? 1, 2, 3 electrons. And remember, we said that we do absolutely need some kind of source of energy to pluck an electron from an atom. In this case, we can use UV light. The way we represent that is with an H and then remember our nu. Here we're just talking about we're using some kind of energy from a high energy source of light or electromagnetic radiation. And what's going to happen is when we say shine UV light on our lithium gas, we're going to eject an electron. And what we're going to be left with is we're going to be left with an electron, 2 electrons in the 1s shell, and we're going to end up with an empty 2s orbital. Okay, so that's just kind of how we can represent what's going on here. And keep in mind that this right here would be the amount of energy that was required to eject this electron here. And, you know, without sufficient energy, we're not going to be able to eject an electron. And we learned a lot about this in the beginning of the year when we talked about the photoelectric effect. And actually, the next video is going to be kind of an advanced look at how do we know this stuff, okay? And that's when I'm going to introduce to you the concept of photoelectron spectroscopy. Kind of a tough one to say. But for now, let's just stick with the basics. So just in a nutshell, we say that ionization energy is just how much energy does it take to remove an electron. Okay, and so far we've taken a close look at trends on the periodic table in this chapter, and so of course this is going to be no exception. Let's take a look at this. We have our periodic table, our S block, our D block, and the P block. And then we're not really going to worry about our F block right now, the lanthanides and actinides, because they actually kind of get a little bit complicated. So let's just stick with our simple view of the periodic table here. Well, if ionization energy is large, okay, if ionization energy is high, that means that it's going to be harder to remove an electron from that atom. We can think about it this way, like if you need a lot of energy to do something, that means that it's no easy task, right? It doesn't take very much energy to just kind of get up and walk around. It's going to take a lot of energy to run around with a set of boxes in your hand, okay? So as the energy gets higher, that means that the task is harder. It's going to be harder to remove an electron. So over here, we say that as we go up the periodic table, okay, as we go from the bottom to the top, our ionization energy increases. And now, again, I'm going to say it again. When ionization energy is high, that means that it's harder to remove an electron. Okay, and so the reason being is that if we look at our N value, okay, our N's are small when we're towards the top of the periodic table, okay? The value, the principal quantum number, so our 1s compared to, say, a 5s or a 5p orbital, okay? Down here, the N value is very large because our N's are going to be over here, remember? Okay, and that's not entirely accurate, but so as the N's are smaller, remember that that means that we are closer to the nucleus. So it's going to be harder to grab an electron that's super close to the nucleus compared to one that's really far from the nucleus, because the nucleus isn't going to have that strong of a hold on that electron. The attraction forces aren't going to be as high as you go away from the nucleus over here. Okay, but as we have our electrons that are very close to our nucleus, it's going to be harder to grab them, okay? So that's why as you go up the periodic table, the ionization energy increases. It gets harder and harder to remove an electron. As we go from left to right, our ionization energy increases. And this has a lot to do with what we've been talking about, our Z effective, okay? Basically the strength of the nucleus. What type of charge is an electron feeling from the nucleus? That's our Z effective, okay? Also keep in mind that we have to consider our inner electrons, our core electrons that are going to be shielding this effect. So an outer electron isn't going to feel quite as strong of a charge from the nucleus because of those electrons in the middle that are kind of blocking or shielding this positive charge. So let's get back on track here. Our ionization energy is going to increase as we go from left to right because, as we saw in the last video, our Z effective is increasing as we go from the left to the right. Okay, so we can think of it as the stronger that our nucleus is, the more of kind of a hold it's going to have on these electrons that we're trying to pluck off of the atom. So if there's a really strong hold on these electrons, it's going to be harder and harder to pluck the electrons off compared to if the nuclear force or the Z effective is lower. Okay, so as the Z effective is increasing, our ionization energy increases. It's going to become increasingly harder to remove an electron. And we can kind of think of this if we take, for example, if we have an element, let's take, say, sodium, for example. We have our sodium is going to be over here, and then our sodium is going to be over here, and then we have chlorine is going to be over here. Now, sodium is going to have a pretty low ionization energy compared to chlorine, which is in the same period. And we can see this because when sodium becomes an ion, we look at our charges on top of the periodic table that we've drawn in, it's going to become a +1 charge. What that means is that it loses an electron. Loses an electron. And that happens fairly easily. So that's a normal charge that we see. What we don't see is this. Okay, we don't see positive chlorine atoms because, let's see, we're all the way over here towards the top. Of course, fluorine is going to be have a higher ionization energy, but we're pretty close to the upper right-hand corner there. So our ionization energy is very high because it's towards the top, but it's also going to be even higher than sodium because remember, as we go from left to right, our ionization energy increases. So we do not see positive chlorine atoms because it's going to be very hard for it to lose an electron. Instead, we see minus charges because instead it's going to gain an electron, which is what we're going to talk about next with electron affinity. But just a couple of notes about this. You can read in your book more of the details, but in general, what we're talking about here is called the first ionization energy. Okay, so we say this is the first ionization energy. Another way to write it would be to put a little subscript here next to the I and the E. And as you continue to pull additional electrons off of an atom, it's going to become harder and harder to do. So the ionization energy for the first electron that's going to come off is generally going to be less than the energy it's going to require to take off the second electron. And then as you go on and on, it's going to become increasingly more difficult to remove an electron the more that you take off. Something your book gets into in pretty good detail that you do need to know is that there are going to be differences with if you're plucking off valence electrons. This general trend will apply that the first one is going to be easier to take off than the second. But as we've exhausted all the electrons in the outer shell, as soon as we start moving into those core electrons, it's going to become even harder to take off. So you do need to know those differences. All right, let's briefly move on to section 7.5, which is which is electron affinity. And we're not going to spend too much time on this, but electron affinity, which we can say is EA, is going to be the energy associated with gaining an electron. So ionization energy was the energy associated with removing an electron. Electron affinity is going to be the energy associated with gaining an electron. And here our values are not always going to be positive. We say that if our delta E is negative, then it's going to be favorable for that atom to gain an electron. So this would be our anions. So we used the example before. We have a chlorine gas. Let's say we have it gain an electron, which we already know that it does because it's going to become a Cl- anion. The delta E associated with that is going to be a negative 349 kilojoules per mole. Okay, so we can tell that that's going to be a favorable reaction. And you can look in your book for other trends about why, for example, noble gases are not going to want to gain an electron. And there are other trends too, depending on the outer shell.